Now this problem is a satellite problem. It says, how long does it take a satellite to do one complete revolution around the Earth if it orbits at 5,600 kilometers above the surface of the Earth? Above the surface of the Earth. So if I draw my picture, I'm going to say that we're going to have a satellite somewhere in here. And guess what? Where that is, that's actually a lot closer than most satellites are. Our satellites that are up in space are not that close. So, but if we did have a satellite there, the only force that would be causing the satellite to change direction would be the gravitational force of attraction between the satellite and the Earth. So I'm going to label that as Fg. So my force equation, when I sum up my centripetal forces, it's going to be Fg. Now it's going to equal either mv squared over r or mr omega squared. Again, if r is the unknown, if they want to know the orbital radius, then I would use mr omega squared. If they give me the angular velocity in radians per second, that might be another reason why I would consider mr omega squared. But neither of those apply here, so I'm going to write that as mv squared over r. So there's my descriptive equation. So if you have the picture and you have that, you're going to get some points. If it's a 10-point problem, maybe 4 out of the 10 points is what I have on the board now. Because there's really not a lot to do in this problem. Well, the next thing I'm going to do is I'm going to replace Fg with the formula for Fg that we went over yesterday. So I am going to say that G, now I know it's M1, M2, but you don't have to use 1 and 2. You can use subscripts. So you can either call E the Earth and S the satellite, or I'm not even going to use a subscript for the satellite. I'm just going to write, instead of M1, I'm just going to write M, but I'm going to write M for the Earth over r squared. So that's what Fg equals. And then on the other side, I'm going to leave just m v squared over r, because this m right here is the satellite's mass, and that's the satellite's mass. So since they're on both sides, you can see that I can cancel them out. So I can cancel them out. So what that means is that if I have a satellite in space at a certain height and it's moving at a certain velocity, it doesn't matter whether it's a megaton object or if it's a pebble. They'll all move at the same, they'll all stay in orbit as long as they're all going at that speed. Because there's nothing out in space that's going to slow it down, so whatever speed it's going at, that's the speed that it will actually orbit the Earth. So now I just want to, let's see, the problem says, how long does it take a satellite to do one complete revolution? I'm going to get that answer from getting the v. Because if I know the v, I can figure out the t. Remember, v, omega, and t, linear velocity or tangential velocity, angular velocity, and time are all related. So if I know one, I know all three. It's just a conversion. So my first step, since I'm really solving for v first, is I've got fractions. The step is when there's fractions, multiply by the least common denominator. So the least common denominator is r squared. When I multiply the left side by r squareds, they cancel out, and I'm left with GME. When I multiply the right side by r squareds, one of the r's cancels, but I'm still going to have one left over, so I get v squared r. And we want to solve for v, so I'm going to simply move the r over and take the square root. So v is going to equal the square root of GME divided by r. And I should get my units as meters per second when I plug in all my numbers. So that's going to equal G, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. All right, that's your G, universal gravitation constant. The mass of the Earth, which is also on your formula fact sheet, is 5.98 times 10 to the 24th kilograms. And the R, now, okay, the R. The R is not 5,600 kilometers. That's the height above the surface of the Earth. We need the R from the center of the Earth to the satellite. We need the orbital radius of the satellite. So we can't just use the radius of the Earth, and we can't just use the height of the satellite above the Earth. We have to add them together. So if I add up, so my R is going to equal 6.38 times 10 to the 6th meters, plus, if I write 5,600 kilometers in meters, how many meters would I have? How many meters are in a kilometer? What's that? There's 1,000, right? So I have 5,600 times 1,000. That's 5,600,000. So if I write that number in scientific notation, that's going to be 5.6 times 10 to the 6th meters, because I need both of these to be in the same units if I'm going to add them together. And if I add those together, you'd get, well, I could say I get, 11.98 times 10 to the 6th, or 1 point, what do I get if you add those together? Well, this number right here is the height of this, is from there to there. That's the height. It orbits that high above the surface of the Earth. So 5,600, and that's 6,380 kilometers, or 6.38 times 10 to the 6 meters. So if I add these two numbers together, then I'm going to get, what am I going to get? Looks like I'm going to get like 11.98. So if I round that to two significant digits, then I'm going to get 1.20, right? 11.98 would be, to three significant digits, 12 times 10 to the 6th. So that's the same thing as 1.2 times 10 to the 7th meters. 12 times 10 to the 6th is the same thing as 1.2 times 10 to the 7th meters. So that number is going to go down here. 1.2 times 10 to the 7th meters. It would have been simple if I just wrote this number as 6.4, right? Because they'd have similar number of significant digits. You really, whenever you're adding numbers, you shouldn't have your answer more accurate than the least accurate number you're adding together. And the least accurate number is right there. So, solving this, and what do you get? When you solve for V, what's that going to equal? 5 point what? 5.77 times 10 to the third? Okay. So 5.77 times 10 to the third meters per second. And then the question we want is, how long does it take the satellite to do one revolution? So all I have to do is take that number. I want the time. So I'm going to invert it, because I want the unit of time in the numerator, not in the denominator. So I'm going to write 1 second over 5.77 times 10 to the third meters. And I'm going to, I'm going to do 2 steps here, because the question, I think I asked you to get the answer in hours, right? Not in seconds. So let's actually get that also. So we're going to go from meters to revolutions, and then I want to get rid of seconds, so I need to put seconds down here. So I'm going to go from seconds to hours. 1 hour is 3,600 seconds, and 1 rev is the circumference that the satellite is moving through. So it's going to be 2 pi, and I have to use this number because that's the radius of the satellite. So that's going to be 1.2 times 10 to the 7th meters. And if you solve that, I hope you get like, it's either 3.63 or 3.64. What do you get? 3.63. So 3.63 hours, and we're done.